Okay, here we go. Today is April 13th. Thankfully, not Friday. On your notes, put April 13th. Then put exponential functions, part 2. Even though we sort of had part 1 yesterday, I'm going to review it today. There was no video yesterday, so it'll be a good. This will sort of work to handle 2 days worth of stuff. All right, so exponentials. They're kind of related to geometric sequences, and so I would copy this whole slide. This one really is worth putting into your notes. Okay, so I'll pause for a minute while you just copy this puppy down, then we'll talk about it. Okay, so geometric sequences turn into exponential functions, at least they can, and let's talk about when you have an exponential function, there's something really important. This is also worth putting in your notes. Exponentials have an x in the exponent. So whenever you're looking at a function, they kind of get confusing after a while. There's the square root function, there's all kinds of functions. Exponential functions have an x in the exponent. So I can look at this little function right here and say, oh, it's got to be an exponential function because it's got an x in the exponent. That means that these other two, like the a and the b, those are just numbers. And they tell us something about the numbers here. This a, if I follow the arrow up, it says that's the initial value. So like if we were doing one of those loan or investment problems and we like started out with $10,000 to invest, that's where it would go. The initial value, the starting amount, would go right there in the a. The b is where the common ratio goes, or the thing you multiply by each time. Like for instance, if you're going to get like 7% interest from the bank, dream on. That's like 0.7% interest nowadays, but let's say you're going to get 7% interest. You'd multiply each time by 1.07, and that would be the number you multiply by each time. It's also called the common ratio, and that goes right there. All right, so here's an example of one of these green ones. Do you remember what those are called? There's a certain kind of notation. It is a sequence, so it's a certain kind of sequence, though. What kind of sequence is it? Yes, it's geometric because you're multiplying by something, but it's a special kind of notation that with that whole u sub 0 and u sub n and u sub n minus 1. No, that's not it. Good try. There's a name for it. Recursive. There you go. That's a recursive formula. And a recursive formula, you could take, wouldn't you agree that this is the starting value? It's what you start with in your sequence. So the starting value is supposed to go there. So there it is. And this, the thing you multiply by each time, it's just found right there in your formula. Okay. And that's the thing you multiply by each time, called the common ratio. And it's got an x in the exponent, so it must be a what? Exponential. All right. So that's the main points of what you were supposed to get from yesterday. If I looked at this one, remember how this first number is supposed to be the initial or the starting value? You see how it kind of starts there? Now, granted, they even have a line back here implying that there's more behind it, but you kind of usually consider your starting value at the graph, the y-intercept, or where it starts going from left to right. Okay, so you could say that's the starting value. And this right here is how much it goes up each time, like it's doubling. It goes from 10 to 20, and 20 to 40, and 40 to 80. See what I mean? So it's doubling each time. And it's got an x in the exponent, so it must be an exponential. All right, now one more thing. It says here that the coefficient a is the y-intercept. See how there's this right here, that number right there is the y-intercept. It goes through right there. We'll talk more about that in a minute. All right, next thing, let's take one of these recursive formulas and let's put it into a exponential. See if you really understood what I just told you and what you learned yesterday. You should be able to do this. So I'll pause for a second while you make an exponential function out of this. And by the way, a function usually starts with f of x equals. You could start with y equals, but I think I'd lean towards f of x in this case. Okay, I'm back. How many of you guys are done? Okay, good. If you start with f of x, the next thing after that would be the initial value or the starting value, which is what? 40,000. And then what's this thing in here? The thing you multiply by each time. And what's it called? The something something. Yes, it is a base, but it is the common ratio. There you go. It's the common ratio, and it's the base of this, and now there's always a what in the what? An x in the exponent. All right. Now, how many of you had that right? Good. Then you get yesterday's stuff, pretty much. This is 4 graphs. One of them is y equals 2 to the x, which is kind of your parent of this whole family. And why didn't we use y equals 1 to the x? Because it'll always be 1. Yeah, it's always 1. 1, 1, 1, 1, 1. And so the line would just go like this. So that wouldn't be any good. So we start with this as a parent. And of these, that's this one right here. Then notice it gets steeper and steeper every time. What do you think the other ones are? Y equals what? Yeah, 3 to the x. And y equals 4 to the x. And etc. So basically, the bigger your base gets, the steeper the little graph gets. But what's one spot they always go through? The y-intercept. What's the y-intercept in all these cases? 0, 1. All right, so that spot right there is the y-intercept. Do you remember, I started the year with this, and now I'm coming back to it again for like the 17th time. The y-intercept is where what? X equals 0. So why is this always coming out to be 1? Because x equals 0 at this spot. And if x equals 0, there's a 0 there, there's a 0 there, there's a 0 there, and 2 to the 0, what's that? 1. 3 to the 0, what's that? You get the idea? It's always going to be 1. Unless we multiply our little function by something. Like, let's say we multiplied our little function by 2 in front, or by 3 in front, or by 4 in front. Then this part would turn into 1. This part would turn into 1. This part would turn into 1. But my answer would still be 2 times that, or 3 times that. That's why this number in front is really the y-intercept. So, if I get all those out of there, wouldn't you agree that the y-intercept of all of these ones that are graphed is 1, right? So really there must be a 1 in front of all of these, right? But I don't need to put a 1 times something in front of it, right? All right, so that makes sense that 1 is the y-intercept of all of those. All right, moving on to this one. What's the y-intercept of that one? 2. Because the y-intercept is where x equals 0. And if I stick in a 0 right here, then this whole term right here becomes what? 1. And then it's 2 times 1. And so the answer must be y equals 2 times 1, which is y equals 2. So the y-intercept must be 2. It's just the number that's out in front here. All right, now we're going to think more about that. Go back to quadratics in your head. Remember the quadratics where this number was like how far it was shifted a certain way, and this one's how far it's shifted a different way. Remember what I'm talking about? So what's that minus 5 do to my quadratic? Down 5. What about the plus 3? Left 3. And when we had even more complicated ones, this is an absolute value one, you knew what all those numbers did to it, right? Things would get stretched or flipped or... Okay, and remember the main theme was that stuff on the outside was up-down stuff, and the stuff on the inside was left and right stuff. We still got that same kind of theme going on when we look at one of these. First of all, prove to me that this is an exponential. It's got an x in the exponent. Good. All right. Now, if I'm going to try to figure out where it's been moved from the parent location, I can look at a whole bunch of stuff like the stuff on the outside. That tells me stuff that's been done up, down. Okay? So like that plus 8, what's that do? Up 8. What's this do? It's a stretch, an up-down stretch. And what's that negative do? It's a flip. What kind of a flip? An up-down flip. Everything's up-down on the outside. What's up-down flip mean? Over which axis? The x-axis. All right. And then the stuff in here is left-right stuff. And so that minus 4 is easy. That's just 4 to the right. And then this is it half as wide or twice as wide? twice as wide because it's counterintuitive stuff that's right by the x.